Hello. Now that you have a fair understanding of the structure of an atom, we can now talk about nuclear reactions. That is, reactions that can happen inside the nucleus of an atom. Now, one such reaction is natural radioactivity. What is radioactivity? Now, unlike the name suggests to a layman, radioactivity has nothing to do with radio. In fact, it has everything to do with radiation. So radioactivity actually talks about radiations that are given out from the nucleus of an atom. Alright, why does that happen? Let's talk about that. Now, let's do a review of atomic models that we talked about earlier. The nuclear model of the atom developed by Rutherford and others suggests that most of the atom consists of empty space with a central nucleus. Is that right? Most of the mass of the atom is concentrated in the central nucleus. The nucleus is now understood to be composed of protons that are positively charged particles and neutrons that are electrically neutral, and both have almost equal mass. And I showed you the masses of those two particles, which is little heavier than the other. Neutron is a little more heavier than the other. And I told you a secret that time, which we're going to use in here, that a neutron can sometimes split into a proton and an electron. And now remember, whenever a particle splits into two pieces, they always emit energy. Why? Because in order to hold particles together, you have energy. When you separate them, the energy that holding them together is released. The energy that holds particles together in a nucleus we call binding energy. So when you separate them, that energy is given off. So whenever a neutron splits into a proton and an electron, a quantum of energy is given out. As radiation. So radiations that are given out from the nucleus causes what we call natural radioactivity. So here is the nucleus that contains protons and neutrons. The red ones are protons and the green ones are neutrons. Protons and neutrons together are called nucleons, you know these, or nuclear particles. Now, elements differ in the number of protons and neutrons in the nucleus of their atoms. That is the basic difference between different elements. The simplest element is hydrogen. Now, how many protons hydrogen has? Hydrogen has just one proton in the nucleus and no neutron. But you know that we talked about the isotopes of hydrogen. You can have different types of hydrogen. One proton and one neutron. What do you call that type of hydrogen? It's called a deuteron. One proton and two neutron makes tritium. There are three different isotopes of hydrogen. But the fact that the nucleus contains only one proton makes them all hydrogen. Alright, now you also know this, the atomic number represented by Z is the number of protons in the nucleus. The atomic number of hydrogen is 1. Its nucleus contains one proton. The mass number is the number of protons and neutrons. Now here I have a nucleus that contains 3 protons and 3 neutrons. Can you recognize that nucleus? hydrogen has 1 proton, helium has 2 protons in the nucleus, the third element is lithium. This is lithium that has 3 protons and 3 neutrons, therefore its atomic number is 3 and its mass number is 6. So Z is the total number of protons and A is the total number of protons and neutrons in the nucleus. And therefore the number of neutrons in the nucleus can be obtained by taking away the number of protons from the total number, N equal to A minus Z. The nuclear symbol, you know how to do this, I have given it to you earlier. The nuclear symbol consists of 3 parts. The symbol of the element, the atomic number, and the mass number. So how do you write this for lithium? The symbol for lithium is Li. Its atomic number is 3. We write it at the left bottom corner. Mass number is 6. We write at the left upper corner. Now here is an example of the nuclear symbol. Li36. Is that right? This is lithium of atomic number 3 and mass number 6. All these are review. We did this already. Now here is another element. This is the nucleus of nitrogen. Now remember, in this lesson we will only talk about nuclei of elements. So the nucleus of nitrogen contains 7 protons. Can you tell me how many neutrons? The atomic number is 7. The mass number is 15. So how many neutrons are there in the nitrogen nucleus? It will be 15 minus 7, that is 8. So there are 8 neutrons, 1, 2, 3, 4, 5, 6, 7, 8. And there are 7 protons and 8 neutrons in the nitrogen nucleus. Well, we also talked about unstable nuclei. You remember that one? Yes? Let's repeat that one more time. Atoms with too few neutrons or not quite enough neutrons sometimes exist for a while, but they are unstable. Now, an unstable nucleus cannot exist in that unstable state for a long time. It has to achieve stability. So what does it do? Well, does it mean that elements can't have more than one stable isotope? No, we talked about that. Ordinary hydrogen, deuterium, and tritium are both stable isotopes. Now, all the elements beyond bismuth, Z equal to 83, are unstable. We again talked about that. Now, unstable atoms are radioactive. What does that mean? We talked about that again. An unstable nucleus would want to achieve stability. How? By throwing away nuclear particles. But remember, every time you throw away nuclear particles, you also have to throw away the energy that hold the particles together. Okay. Now, unstable nuclei, unstable atoms are radioactive. Their nuclei change or decay. What's the meaning of decay? Decay means to degenerate. Is that right? To change into something else. So throw away part of the nucleus and decay into something else. By spitting out particles or radiation, or both. So an unstable nucleus can spit out particles, also electromagnetic energy. Now all these things are part of the radiations that are emitted by unstable nuclei in order to achieve stability. Now, So radioactivity, how do we define radioactivity? Let's give a definition for radioactivity. Radioactivity is the spontaneous emission of particles. Now, that word spontaneous is important. There is no incentive coming from outside. The radioactivity, that the radiations emitted by a radioactive nucleus is spontaneous. It happens naturally on its own without any prodding from outside. Radioactivity is the spontaneous emission of particles or energy. So these radiations can be particles or they can simply be quantas of energy from an atomic nucleus as it disintegrates. Disintegrates means break into pieces, is that right? As it disintegrates into nuclei of another element. You see, when one nucleus emits a radiation that consists of particles, you are losing nuclear particles. If you lose a proton, then that nucleus does not belong to that element anymore. The nucleus then belongs to another element. So as a result of this radiation given out by a nucleus, that nucleus will disintegrate into the nucleus of another element. Well, that process needs to be understood. We will talk about that. Radioactivity was discovered by somebody called Becquerel while experimenting with X-rays and photographic plates. Now, you know that in the early days, pictures on photographic plates were used a lot to study radiations, because a photographic plate will be affected when radiations fall on it. So Becquerel was actually working with photographic plates in studying radiations. Now, how did he come about the discovery of radioactivity? In March of 1896, during a time of overcast weather, Becquerel found he couldn't use the sun as an initiating energy source. Very often the energy from the sun is used as an initiating energy source in many experiments. And so, what did he do? Well, this is the famous Becquerel. Now, he wrapped photographic plates away in a darkened drawer along with some crystals containing uranium. So, he put away some photographic plates along with some crystals containing uranium in a dark drawer. Now, what happened when he took them out later on? Much to his surprise, the plates were exposed during storage by invisible emanations from uranium. Now, a photographic plate can be exposed only if radiations are allowed to fall on it. When light falls on a photographic plate, it changes, right? That's how we get pictures. Now, how did the photographic plate get exposed when it was stored away in a dark drawer? The only explanation that Becquerel can find was this is the culprit. Now, along with the photographic plate, he also packed crystals of uranium. You see, look at the way the mind of a scientist works. He said, these crystals of uranium must have been giving out some radiations. We call those emanations. Emanations are things that come out of something. So the photographic plate must have been affected by emanations given out by the uranium crystal. And that's what his explanation was. The emanations did not require the presence of an initiating energy. In fact, whatever came out from the uranium crystal did not require any external prodding. It happened just like that, spontaneously, on its own. Later, Becquerel demonstrated that radiation emitted by uranium shared certain characteristics with X-rays. Now, those days, before the discovery of radioactivity, X-rays were known. X-rays are very high energy electromagnetic radiations. They can penetrate through your body. Now, studies made by Becquerel showed that the radiations that are given out by this uranium crystal has something in common with those X-rays. In other words, the radiations that are similar to X-rays did come out from uranium. Now, therefore, he made some studies. Well, for his study on radioactivity, Becquerel was awarded the 1903 Nobel Prize for Physics. All right, let's look at what Becquerel did with these radiations. Now, working in the Becquerel lab, Marie Curie, look at some two important names associated with the study of radioactivity. Marie Curie and Pierre Curie, they were husband and wife. Now, for them, it became a lifelong study of radioactivity. Now, this is Marie Curie and this is Marie and Pierre. Mary wrote, "The subject seemed to us very attractive, and all the more so because the question was entirely new." You see, this is what ticks off scientists. When you get a new clue, they get hung on to it and they spend days and weeks and years. In fact, Marie and Pierre Curie worked years of their life studying radioactivity. And you know what happened at the end? These radiations they were studying were so deadly that they both actually died of cancer caused by these radiations. Now, she is best known as the discoverer of the radioactive elements polonium and radium. Do you recall polonium? I talked about Rutherford actually used polonium as its source for alpha particles, which he used as bullets to bombard the gold foil. Also, if you keep watch on the news, the Russian spy Alexander Litvinenko, you recall that name? I think about 6 months ago, Alexander Litvinenko, a Russian spy who was living in England, was actually poisoned by another Russian spy, I believe, or many people believe, using polonium. He was poisoned by polonium. In fact, his coffee was poisoned with polonium. Only a minute fraction of polonium is enough to kill you. If you ingest it, these radiations that are now being produced from within you will actually make all your organs will be bombarded with these radiations, that within days you will be killed. In fact, Alexander Litvinenko died a very painful death. I think it happened in about last 5 months. The inquiry is going on that death. So polonium and radium are very highly radioactive materials, and Marie Curie worked mostly on those. In fact, radium was discovered by Marie Curie. Becquerel analyzed the radiations. So what kind of experiments did Becquerel do using these radiations? Now, what he did is he used the magnets, like the magnet I just showed you. You remember the magnet I just showed you? Let me see if I can separate that. Well, it's protested heavily. Now, this is the magnets that Becquerel actually used. Here, this is the pole pieces. If you look at that, the same pole pieces. and if you allow the radiations to go through. Now remember, the radiations, if the radiations consist of particles, particles carry electric charge, is that right? Protons carry a positive charge. Electrons carry a negative charge. Now, when charged particles are allowed to go in a magnetic field, that is the space between the pole pieces of a magnet, these electric charges will experience force. Now, if positive charges experiences a force to the left, negative charges will experience a force to the right. So, what did Becquerel actually see? Now, this is the radioactive sample, which is polonium or radium. Now look, it is kept inside a lead block. Why is the sample kept inside a lead block? Because the radiations are so deadly. Lead will absorb all these radiations. That means you can be safe. The radiation is allowed to come out only through a small hole. And that radiation that goes through the magnetic field, Becquerel found that the radiations actually consist of 3 types of radiations. One type is deflected to the left, the second type was deflected to the right, and the third type did not deflect at all. Well, what does it mean? It means if the ones deflected to the left are positively charged particles, the one deflected to the right are negatively charged particles, then the one that is not deflected are not particles. They are simply energy. And they cannot be, energy packets cannot be bent by magnetic field. In other words, if I pass a beam of light through this magnetic field, it will not bend. It will simply go straight. So, the radiations given out by a radioactive nucleus therefore consist of 3 types of radiations. So he identified 3 types of radiations. What are they? One of them consists of massive particles carrying a positive electric charge. Well, now you know from our discussions that this green track and this purple track, the one to the left and one to the right, are particles, charged particles. Can you look at these tracks and tell me which of them are more massive? Is the green ones or the purple one? Which is more massive? You see, if a particle is more massive, the deflection will be less. If the particle is less massive, the deflection will be more. Obviously, because these purple ones bend more, we would assume that these purple ones are light particles and these green ones are heavy particles. So, one of them consists of massive particles. We can assume that these are the ones he is talking about, carrying a positive electric charge. You see? So the radiations that are coming from the nucleus, one of them consists of massive particles carrying positive charge. A second type consists of negatively charged light particles. So if these green ones are positively charged, the purple ones are negatively charged light particles. Well, we'll talk about them as we go on. And a third type of radiation was not affected by the magnetic field. Obviously, it means the third type of radiation is not made up of charged particles. That means they are made up of high energy electromagnetic radiations, like X-rays. Now, what are some of the electromagnetic radiations that you are familiar with? Remember, electromagnetic radiations come in all kinds of energies. At the very low energy, you have radio waves. As the energy increases, you have infrared, visible light, ultraviolet, X-rays, gamma rays. You see, gamma rays are the most energetic of all the electromagnetic radiations. All right. So, when a radioactive nucleus disintegrates, in other words, decays, what are the possibilities? There are three types of radiations. The massive positively charged particles were called alpha particles. Just like we sometimes call ABC. When you don't want to give any specific names, you simply call them XYZ or ABC. In the same way, these radiations, instead of giving them any specific name like Emily, John or Robert, the scientists simply call them alpha, beta and gamma. The positively charged particles were called alpha. The negatively charged particles were called beta. And the energy, the electromagnetic energy, is called gamma. Well, that is the very high energy gamma radiations. Now, alpha radiations consist of 2 protons and 2 neutrons. In fact, alpha radiation is a big chunk of the original nucleus. A big chunk breaks away and just flies away. Just like a family breaking away, is that right? A family of a husband and wife and 6 children, all of a sudden somebody, well, a wife or a husband decides, I'm going to go away to create stability in here. Well, we know in our society this is common. Well, here an alpha particle, when it breaks away from the nucleus, it's actually a chunk of the nucleus. It consists of 2 protons and 2 neutrons. What is the nucleus that contains 2 protons and 2 neutrons? The nucleus that contains 2 protons and 2 neutrons is the nucleus of helium. That's right. So, an alpha particle, let's call alpha radiation an alpha particle because it is a chunk of particles. Alpha particle is actually a helium nucleus. So, alpha particles are helium nuclei. It consists of 2 protons and 2 neutrons. Look at this. From the original nucleus, if it emits an alpha particle, that nucleus now loses 2 protons. That means this nucleus does not belong to the original element anymore. It now belongs to another element. That's why we call it nuclear decay. So alpha particles are helium nucleus. Here we got the helium nucleus going away from the nucleus. When the nucleus of an alpha, of an element of atomic number Z, watch this, when the nucleus of an element of atomic number Z emits an alpha particle, it loses 2 protons, right? That means it loses 2 protons and 2 neutrons. The remaining nucleus will have therefore an atomic number 2 units less and mass number how many units less? The mass number is the number of protons and neutrons. The mass number now is 4 units less. So what remains is the nucleus of another element with atomic number 2 units less, Z minus 2, and mass number 4 units less, A minus 4. That is an important concept you need to learn. For example, watch this. Plutonium 94-239. Now this is another way to write the atomic number. You see, when I type, it's easier for me to write like this. I must actually write this 94 on the left side. But when typing, it is rather difficult to do that. So I wrote it on the right side. And read it like this: plutonium-239. You don't need to read the 94 because when you say plutonium, the atomic number is 94. You see, it is the atomic number that identifies the element. So, plutonium with an atomic number 94 and mass number 239, if it emits an alpha particle, the atomic number of the remaining nucleus will be 2 units less. 94 minus 2 will be 92. And the mass number will be 4 units less. 239 minus 4 is 235. Now, the element with atomic number 92 is called uranium. That means a nucleus of plutonium, when it emits an alpha particle, what remains is the nucleus of uranium. We say that plutonium decays into uranium. Alright, here I have an animation of that. Watch it one more time. This is plutonium-239. It emits an alpha. Watch it. There goes the alpha. 2 protons and 2 neutrons. What is left behind is uranium-235. So, what is left behind is uranium-235. Plutonium-239 emits an alpha, leaving behind uranium-235. Alright, look at the way we write this as an equation. Plutonium-94-239 emits an alpha. Alpha is written as alpha 24, and what is remaining is uranium-235. Look at that. If you add this 2 to 92, you get 94, and add this 4 to 235, you get 239. Plutonium-239 decays by emitting an alpha and leaving behind a nucleus of uranium-235. In a similar way, I can write radium of atomic number 88 and mass number 226 emits an alpha particle and becomes the nucleus of a radon of atomic number 86 and mass number 222. You see that? When it emits an alpha particle, the atomic number becomes 2 less. From 88, it comes down to 86. And the element with atomic number 86 is radon. And the mass number is reduced by 4 units. Now this is radium of atomic number 88 and mass number 226. It emits an alpha. What happens? You are now given left with radon of atomic number 2 units less of 86 and mass number 4 units less. So radium-226 gives off an alpha, leaving radon-222. Now this is basically alpha decay of how an element decays after giving out an alpha radiation. This nuclear reaction can be represented by, look at the relationship I'm going to write, radium-88-226 emits an alpha. When an alpha is emitted, the atomic number is going to be decreased by 2. So the element left over is radon of atomic number 86. The mass number is going to be reduced by 4. 226 minus 4 is 222. Okay. Now, what is the process of beta emission? Beta radiations consist of fast-moving electrons. So alpha radiations are heavy particles that can consist of 2 protons and 2 neutrons. But beta radiations are fast-moving electrons. Now the question is, where did an electron come from the nucleus? Is there any electrons in the nucleus? In our atom model, we always said electrons are outside the nucleus, not inside the nucleus. But radioactivity is the disintegration of a nucleus. Are there electrons in the nucleus? Well, this is where I'm going to use the secret that I told you. What's the secret? A neutron inside the nucleus can split into a proton and an electron. The proton will stay in the nucleus, the electron will go away as a beta radiation. Well, that is the mechanism that's going to happen. So when a nucleus emits a beta radiation, what goes out is an electron. Remember, therefore, if a beta or an electron has to be emitted, a neutron is going to become a proton and an electron. So at the expense of a neutron, a proton is created, and the electron, that is the byproduct of it, goes out of the nucleus. Now, radiations are emitted from the nucleus. Can a nucleus give out an electron? A neutron degenerates into a proton and an electron, like this. Look at the way I write a neutron. A neutron is N01. Remember, this is supposed to be the atomic number place, which is the number of positive charges. Is that right? Atomic number is the number of positive charges. And neutron is neutral, it has no charge, so we write 0 there. And its mass number is 1, because mass number is the number of protons plus neutron. So look at the neat way we can write a neutron. A neutron is its charge 0, its mass 1. Now a neutron turns into a proton. The moment it turns into a proton, it now has a charge 1 and the mass 1, and also an electron. The electron is emitted. Proton stays in the nucleus and the electron gets emitted as a beta. So what happens inside the nucleus when a beta radiation is emitted? The number of neutrons now become less by 1. But at the expense of that neutron, a proton is created. So the number of protons is now increased by 1. Now remember, the number of protons is what determines the atomic number. So the atomic number of the nucleus that remains increases by 1. So you go one step higher when you emit a beta radiation. This increases the atomic number by 1, and the mass number will not change. Why not? Because the additional proton is created by the existing neutron, and mass number is the number of neutrons plus the number of protons. If a neutron is changed into a proton, the total number of neutrons and protons will not change. Therefore, when a nucleus emits a beta radiation, what happens? Its atomic number increases by 1, but the mass number remains the constant. Now, look at the example. Carbon atomic number 6 and mass number 14 emits a beta, an electron. And what is the charge of the electron? -1. Its mass is 0. What is left behind is nitrogen of atomic number 7. The number of protons increases by 1. The atomic number of the resulting nucleus is 1 unit greater, and the mass number remains the same. When carbon 14, you understand when I call it carbon 14, I don't need to call out the atomic number, because when I say carbon, it's understood that the atomic number is 6. Why? Because atomic number identifies the element, whereas mass number can change depending on the isotope. So we say carbon 14. Carbon 14 is an isotope of carbon. Most abundantly available carbon is actually carbon 12, which has 6 protons and 6 neutrons in the nucleus. So this is not the common carbon. This is a rare carbon. This is carbon 14. Now this is radioactive, and it emits a beta radiation, becomes nitrogen 14. In the same way, I told you about an isotope of hydrogen with 2 protons in the nucleus. Look at this. H13 is that isotope of hydrogen, tritium. Now that will give out a beta radiation. Tritium is unstable. Tritium is not a stable isotope of hydrogen. So tritium, which has 1 proton and 2 neutrons, gives out an alpha, leaving a nucleus of helium. Look at this. Atomic number increases by 1. Mass number remains the same. So the isotope of hydrogen, hydrogen 3, gives out a beta radiation, leaving behind helium 3. A nucleus of helium is left behind. Beta emission can also occur in another way. You see, if a neutron can split into a proton and a negative electron, a proton can split into a neutron and a positive electron. Well, this is news for you, is that right? Can an electron be positive? Well, apparently there is a particle that is very similar to electron but carrying a positive charge. That particle is called a positron. It is not an electron. An electron always carries a negative charge. A positron is like an electron in its mass, but it carries a positive charge. So how can a positron be produced? Sometimes a proton can change into a neutron after emitting a positron. You see? Alright, a positron is a positively charged electron. Well, a positive electron. Well, we better call it the positron. So a beta can also be a positron. Although most of beta emissions are negative electrons, there are beta emissions that are positive electrons. A proton degenerates into a neutron and a positron, emitting also a massless particle called neutrino. Don't worry about that. At the moment, you concentrate on this. A proton, look at the way I write the proton. Proton has 1 positive charge. Its mass number is 1. Proton is 1, 1. Emits a positron, an electron with a positive charge, leaving a neutron behind. Alright. When this happens inside the nucleus, what happens? You see, the proton now becomes 1 less, and the mass number will not change because a proton changes into a neutron. So beta plus So from now on, we will characterize the beta as a beta negative or a beta positive. A beta negative is a negative electron. A beta positive is a positron. Well, what happens inside the nucleus when a beta positive is emitted, when a positron is thrown out? The beta positive is the result of a proton becoming a neutron. That means the atomic number will now decrease by 1 because the number of protons is now 1 less. But the mass number will not change because that proton has changed into a neutron. The sum of protons and neutrons will remain the same. So once again, what happens when a negative beta is emitted? When a negative beta is emitted, atomic number increases by 1. When a positive beta is emitted, atomic number decreases by 1. All right? Is it possible for you to keep track of this? Is it getting too complicated? Well, let's see. Now, copper 64. Look at this. Copper, again, I don't need to read that 29 because when we say copper, we know its atomic number is 29. 64 is its mass number. So I'm going to read copper 64 emits a positive electron, leaving behind nickel 64 of atomic number 28. When a positive electron is emitted, the atomic number decreases by 1. Copper, after emitting a positive electron or a beta plus, becomes a nucleus of nickel of atomic number 28. You see, look at the way nature operates. Isn't that beautiful? All these transformations that can happen. So we write it like this. Copper 2964 gives out a positive electron, leaving behind a nickel of atomic number 28 and mass number 64. I told you this is written for convenience. The atomic number 29, instead of writing to the left, I write to the right because it is easy for me to type that way. Well, even in books you will see this kind of representation, so that's not unusual. Another positive electron emission, another beta plus, sodium of atomic number 11 and mass number 22 emits a positron or a beta plus, becomes neon of atomic number 10 and mass number 22. When a positive electron is emitted, the atomic number reduces by 1. I don't want you to learn these equations. I'm just writing down for explanation's sake. But I want you to understand one thing from all these discussions that I have done so far. When a nucleus emits an alpha radiation, what happens to the remaining nucleus? The remaining nucleus will be 2 units less in its atomic number and 4 units less in its mass number. Alright? What happens when a nucleus emits a negative electron, a negative beta? When a nucleus emits a negative beta, its atomic number increases by 1. The mass number remains the same. Similarly, when a nucleus emits a beta positive, a positron, the atomic number decreases by 1, but the mass number remains the same. I want you to know this. Alright? Then you can answer simple questions based on that. Gamma radiations are, of course, not particles. They are very high energy electromagnetic radiations. So one more time, Alpha radiations are massive particles. They are made up of 2 protons and 2 neutrons. They carry a net positive charge. Beta radiations are negatively charged electrons or positively charged electrons. They are electrons either carrying a negative charge or carrying a positive charge. So alpha and beta are both particles, but gamma are not particles. They are simply very high energy electromagnetic radiations. Gamma radiations or X-rays frequently accompany the emission of alpha and beta radiations. Whenever a mass splits into pieces, the energy that holds them together comes out. And gamma radiation, the origin of gamma radiations is like that. So gamma radiations are very often accompanied by the emission of alpha or beta radiations. Now look what happens when a nucleus emits a beta. When a nucleus emits a beta negative, means a negative electron, the remaining nucleus will have an atomic number 1 unit greater, and it also gives out a copious amount of gamma radiations. So here, once again, those 3 radiations. Alpha radiations are helium nuclei, 2 protons and 2 neutrons. Beta radiations can be electrons or protons. And gamma radiations are not electrically charged. They are not deflected by electric or magnetic fields. Now, if a radiation is deflected by electric or magnetic field, it indicates that the radiations carry electric charge. Now, gamma radiations are not electric charges. They are simply packets of energy, and they are not deviated by a magnetic field. Gamma radiation is able to travel many meters in air. In fact, gamma radiations are deadly. If I have a polonium or radium sample here which gives off gamma radiations, I am not safe, because those radiations can bombard me, cause a lot of harm to my body. Gamma radiations are very highly penetrating radiations. Now, radioactive materials that emit gamma radiations and X-rays constitute both external and internal hazard to humans. If you ingest this radioactive material, well, there is no hope for you. Just like the Alexander Litvinenko, who was poisoned, who died a miserable death, that is destined if you ingest these poisonous radioactive materials. Now, dense materials are needed for shielding from gamma radiations, and that's the reason why very often these radioactive materials are kept in very thick lead boxes. You see, lead is very, very dense, and so these radiations can be stopped by few centimeters of lead. Now here I have a thin sheet of aluminum. Now if I have a gamma radiating source here, this aluminum will not stop it, but this thick piece of lead might stop it. You see, lead is very dense, and so it might stop it. So it is very important to keep these materials that are radioactive in thick shields of lead. Now let's talk about relative penetration ability of radiations. So which of these radiations is more penetrating? What do you think? Which of them is more penetrating? Alpha radiations, remember, alpha radiations are massive particles. Beta radiations are light electrons. Gamma radiations are high energy electromagnetic radiations. Alpha is the least penetrating of all the radiations. In fact, alpha radiations can be stopped by a thin sheet of paper. If you want to block alpha radiations reaching you, you can block them by a thin sheet of paper. Now here I have drawn some relative comparisons of what kind of shielding is needed for these radiations. Alpha radiations are stopped by a thin sheet of paper. Beta radiations can be stopped by a thin sheet of aluminum like this, the one I showed you. Now, gamma radiations will penetrate both paper and aluminum. Look at that. But it can be stopped by a fairly thick sheet of lead. So, beta rays are more penetrating than alpha rays and can be stopped by few millimeters of aluminum. They are very fast moving electrons. Gamma rays are the most penetrating and they can be stopped only by few centimeters of lead. Radioactivity is the result of instability within the atomic nucleus. Is that right? We know that. If a nucleus is stable, there will be no radiations. Now, when the nucleus gets very bulky, in other words, it is determined by the ratio of neutrons to protons. If the nucleus contains too few neutrons or too many neutrons, it will be unstable, right? Yes. The stability of a nucleus is determined by the ratio of neutrons to protons. In other words, if the ratio is not the right value, the nucleus may be unstable. Now here I have a diagram of that ratio. Now the graph is actually the number of protons against the number of neutrons. Now look at this line. What does that line indicate? Along that line, if you take any point on that line, look at where I'm pointing now. 30 protons and 30 neutrons. Look at another point. 60 protons and 60 neutrons. Look at another point on that straight line. 90 protons and 90 neutrons. So this line is called a 1-to-1 ratio. In other words, the ratio of neutrons to proton is 1. The number of neutrons equal to the number of protons. You see, if you look at lighter elements, that means hydrogen, helium, lithium, carbon, boron, and so on, those lighter elements which have less number of protons, the number of neutrons and protons are almost the same for stability. Now, this indicates the stability band. You see, stable isotopes. What that means is, as the nucleus becomes heavy, a 1-to-1 ratio is no longer stable. In order that you may keep a heavy nucleus together, when the number of protons increases, in order to keep them together, you need a larger number of neutrons. So as the nucleus becomes heavier and heavier, you need a larger number of neutrons to keep the nucleus stable. That means the ratio has to be more than 1. The number of neutrons divided by the number of protons has to be greater than 1. That is what this indicates. So heavier elements require a ratio greater than 1. You understand what that means? A ratio greater than 1? It means it needs more neutron than protons. Now, look at an element here where I'm pointing. If it has 40 protons, it requires 50 neutrons for stability. Now, this is called a stability band. That means an element here which has 60 protons requires 90 neutrons to keep stability within the nucleus. As the number of protons increases, you need greater number of neutrons to keep peace. Alright, look here. An element of atomic number 80 requires almost 120 neutrons to make that nucleus stable. So heavier elements require a ratio greater than 1 for stability. Neutrons provide additional attractive nuclear forces. You see, I told you the forces that keep the nucleus together are called strong forces. And these strong forces are now enhanced by the greater number of neutrons. But there is a limit to this additional attractive force. That means as atomic number increases beyond 83, look at this, the stability band finishes by atomic number 83. So, if the number of protons now keep on increasing up to 83, we can create stability by increasing the number of neutrons. But you cannot keep on doing it indefinitely. That means any element above atomic number 83, I hope you can see where I'm holding my pointer. Z equal to 83, the number of protons, 83 in the nucleus. Any element that contains greater than that many protons is always unstable. No number of neutrons can create stability there. No counseling will help in that situation. You've got to break it down. You see that? It's got to disintegrate. Now, elements to the left of the band of stability. Now, suppose you have, well, you know that some element emits alpha, some elements emit negative electrons or negative beta, and some others emit positive beta. Now, what are the circumstances which decide what kind of radiation is going to be emitted? Now, if you look at an element over here where I am pointing, tell me, if an element is here, it contains more neutrons than protons. Is that right? That means neutrons need to now become proton. Neutrons are going to be made into proton, and when a neutron becomes a proton, it also generates an electron. So an element anywhere here to the left of the stability band will always decay with a negative beta. So beta emission, I have taken a part of this and magnified it here. So the blue is the stability band. If an element, if a nucleus is along the blue line, it is stable. You see, this is stable, but if it is in the red region, it is unstable. A nucleus here is going to give off a beta emission. When a beta is emitted, the number of neutrons become less, the number of protons increases, the element now falls back to stability. On the other hand, if an element is here, what happens? It has got less number of neutrons than required. So an element here on the right of the stability band is going to emit a positive electron, so that a neutron changes into a proton, again taking the element back to the stability band. On the other hand, look at elements here. colored in gold. That is where there are too many neutrons, so these elements will give out alpha radiations. So look at these again. If elements are to the left of the stability band, all these elements here indicated by red, they will give out beta negative electrons. And these electrons to the right give out positive electrons, positrons, and these electrons are these elements that are way to the right of the stability band will emit alpha radiations, and all these radiations will help the elements to get back to stability. The idea is ultimately to achieve stability. Elements to the right of the band of stability emit beta plus to increase the number of neutrons. And elements further down will be emitting alpha radiations. All radiations move isotopes closer to the stability band. Once an element is in the stability band, it will not radiate anything. A nucleus with atomic number greater than 86 will emit an alpha particle and still have atomic number greater than 83. You know that if the nucleus contains more than 83 protons, it is unstable. So if you have an element that contains 86 protons, it is unstable. If it emits an alpha, the atomic number will be reduced by 2, that will be 84. That means one radiation is not enough to achieve stability. In order that certain nuclei may achieve stability, it may have to give off a series of radiations. Well, we will look at that in a minute. The process will continue through a series of decay until a stable nucleus is achieved. Now that's what happens in nature very often. All radioactive isotopes tend to emit radiations successively until the end product is a stable isotope. A stable isotope with atomic number less than 83. For example, uranium, when I say uranium, you know that the atomic number is 92. An isotope of uranium, uranium-238, this is the very abundantly available isotope of uranium. Is this stable? No, its atomic number is 92. Any element with atomic number greater than 83 is unstable. So uranium-92-238 is an unstable nucleus. It decays by 5 successive emissions of alpha. You see, one alpha followed by another alpha followed by another alpha. It emits 5 successive alpha and then followed by a beta, beta and an alpha. How many radiations? Altogether 5 plus 3, 8 radiations, and ultimately it will become an isotope of lead which will be stable. Now you can see uranium goes through this series of radiation before it can become stable, and this is called radioactive series. And these radiations, how many radiations for uranium? 5 plus 3, 8. And those 8 radiations are called the uranium series. The uranium series. I'm going to show you those series. Again, you don't worry about it. It's too complicated for you. But try and follow what I'm saying. Uranium series. We start with uranium-92-238. Now, once you understand these steps, then you understand what happens when an alpha is radiated, a beta is radiated, and so on. So, what happens when a nucleus emits an alpha? Its atomic number is reduced by 2, mass number is reduced by 4. And therefore, the resulting nucleus is thorium of atomic number 90, mass number 234. Uranium-238 emits an alpha radiation, leaving the nucleus of thorium of atomic number 90 and mass number 234. Now, this is unstable, alright? What does thorium do? It emits another alpha radiation. What is left behind? An element of atomic number 2 units less is 88. That is radium-88 230. So thorium 90 234 emits an alpha, leaving behind the nucleus of radium-88 230. Well, radium is again radioactive. Radium-230 emits an alpha, leaving behind an isotope of radon of atomic number 86 and mass number 226. Radon is again alpha active. It gives off an alpha radiation, producing an element 2 units less. That will be polonium. Polonium-222. Polonium is alpha active. It gives off an alpha, producing an element of atomic number 2 units less than 84. 82. The element with atomic number 82 is lead. So, after emitting 5 successive alpha, you have now come to an isotope of lead of mass number 218. But this isotope of lead is not stable. It is going to give off a negative beta, going one step higher. Remember, a negative beta will increase the atomic number by 1, will keep the mass number the same. So now you have lead become bismuth of atomic number 83 and mass number 218. And this is again beta active. Look what happens. Bismuth 83 218 gives off a negative beta. That means the resulting nucleus will have atomic number 1 unit more. So you now end up with another isotope of polonium. You see? So first we had this isotope of polonium. And now you have a different isotope of polonium. And this polonium gives out an alpha, giving out this stable isotope of lead. Here, lead-82-214 is stable. And this series of radiation is called the uranium series. Okay, let's now move on. Let's now talk about half-life of a radioactive element. Half-life of a radioactive element. What does that mean? Now, suppose I have a sample of radioactive material here. Now, this is a sample of radioactive material. Now, suppose this is 10 grams of uranium. Now, you know that when one nucleus of this disintegrates, that nucleus is no longer uranium, but it belongs to thorium. So, if I have a sample of uranium, as more and more nuclei of uranium undergoes disintegration, you have now more and more thorium atoms are created. So what I'm now holding is a combination of uranium and thorium. Now let me ask you, suppose this sample of uranium, but this is not uranium, suppose this sample of uranium contains just 1 million atoms. That means 1 million nuclei. Now, will all those nuclei of uranium undergo the decay, undergo the radioactive decay all at once? Well, the answer is no. You see, radioactivity is a random phenomenon. You don't know when exactly a nucleus is going to disintegrate. Now, it decides on its own when to do it. So, a uranium-238 nucleus is sitting here doesn't mean it will disintegrate immediately. It might disintegrate now, or it might disintegrate 6 years from now. You see, it can stay in that unstable condition for a very long time. So, radioactivity is a random phenomenon. So, if there are 1,000,000 nuclei in here, out of that, only a very few will undergo disintegration at any given time. You see that? That means the amount of uranium-238 in here will keep on decreasing as radiation being given out. Okay, I want you to understand that concept in order to understand half-life. Not all nuclei in a given sample of radioactive material will undergo radioactive decay all at the same time. You see? The number of nuclei that disintegrate per second is called the rate of decay. The rate of decay. How many nuclei undergo disintegration per second? For example, I said let's consider this has 1,000,000 nuclei of uranium-238. Now give me a number. How many out of this 1,000,000 will undergo decay in the first second? Well, not many. Suppose I'm going to say we start with a number. Starting number is 1,000,000. Now let us say every second we have 100 disintegrations per second. Well, so we have a sample of uranium here that contains 1,000,000 nuclei. Not all of them will disintegrate at the same time. Suppose 100 disintegrations happens a second. Now that means 100 of these original uranium have now become thorium. You see that? The original nucleus now contains 100 less uranium nuclei. That means those 100 have now become thorium. So we have only less than 1,000,000 uranium left now. So tell me, will the rate of disintegration keep a constant, or will it decrease, or will it increase? With time goes on, the original radioactive nuclei are going to decrease. That means this rate of disintegration will also decay. So, if I study today, I find 100 disintegrations per second. Tomorrow I take the sample, I find the disintegrations have decreased. I have only 80 disintegrations per second. You see? Today I found there are 100 disintegrations per second. Tomorrow I come and study the sample, I find only 80 disintegrations per second. The day after I come to study, I see only 60 disintegrations per second. And later on, I find only 50 disintegrations per second. You notice that when we started to look at it, there were 100 disintegrations per second. After a certain number of days or after a certain time, the rate of disintegration has become 50. That is exactly half of our original rate. Now, the time taken for the rate of disintegration to reduce to half its value is called the half-life of a radioactive element. So, if in the beginning when you start looking at it, if there are 100 disintegrations per second, the number of days or the number of seconds, you can measure time in any unit, taken for that rate of disintegration to reduce to half its original value is called the half-life of that sample. Every radioactive substance has a fixed half-life. That means the time taken for the rate of disintegration to reduce to half its initial value is a fixed number for every radioactive material. The rate of decay is proportional to the number of atoms present. What does that mean? If there are 1 million atoms present today, if I have a 100 decays happening today, when there are only 500,000 of the original atoms left, the rate of decay will be less. In a large sample, the rate of decay will be you see, the rate of decay will be much greater in a large sample than in a small sample. For example, if I have a sample of uranium here, which is 1 kilogram, suppose the rate of decay is 100,000 per second. Now, if I have 0.5, a half a kilogram, the rate of disintegration will be only 50,000 per second. If I take a quarter of a kilogram of uranium, the disintegrations may be only 25,000 per second. So, if I take 1 kilogram of uranium, if 100,000 disintegrations happen in 1 second. If I take a half of that, 0.5 kilograms, there will be only 50,000 decays happening in a second. So in a large sample, the rate of decay will be more than in small samples. In any sample, the rate of decay slows down with time. As I showed you in my earlier example, as time goes on, this rate of decay will slow down. Now, therefore, what is the half-life? I have if there are a 0 gram of radioactive material when you start counting, the time taken for half of that to decay is called the half-life of that radioactive material. Now here I have a curve showing we start with a quantity A0. I don't know whether you can actually see that on the screen. Let me have a look. I think you can. Well, if you started with A0 gram of a radioactive element, you can see as disintegrations, as time goes on, the disintegrations continue. Now, disintegration continue means the amount of the original substance is now going to decrease. After a certain time, only half of the original amount is present. And the time taken to do that is called one half-life. We will represent half-life by the uppercase T. So the time taken for an original amount of radioactive substance to reduce to half its value is called its half-life. For example, let me see if I can go back to my whiteboard and show that. Suppose you have a lump of uranium here of 238. Now, you started with this when time equal to 0, that is when you start your clock. After a certain time, this has been radiating. Now you have only half of. Suppose I started with 1 kilogram. Now I have only now 0.5 kilogram of uranium-238 left. So in my original sample, I had 1 kilogram of uranium-238. Now after a very long time, the uranium has been decayed. Now remember, when uranium decays, it becomes thorium. Now, after a very long time, the sample contains only 0.5 kilogram of uranium. The rest is now thorium. The time taken for this original amount of uranium to reduce to half its original value is called the half-life. Suppose this time, the time taken for this to happen is, let's say, 6,000 years. 6,000 years. You started with 1 kilogram of uranium. After 6,000 years, the sample only contains half a kilogram of uranium. The other half has now become thorium. The time taken for the original amount of uranium to become half its value is called its half-life. Now, it took 6,000 years for that to happen in uranium. That means half-life of uranium is 6,000 years. That means, you remember I told you I have 1 million grams of uranium in this sample. What is the time taken for that 1 million uranium to become half a million uranium? It will be 6,000 years. You see, in 6,000 years, this sample will have a half a million of uranium nuclei, and the other half will be thorium then. Okay, I hope I explained that sufficiently for you to understand. Now, if A0 is the amount of radioactive substance in the beginning when time is 0, after one half-life, after this much of time, only half of the original amount is present, and that is called one half-life. So after one half-life, only half of the original amount is present. The other half has now become another substance. If you now go for another half-life, one more half-life, only half of this will be left. After 2t, means after 2 half-lives, look at how it goes. If you start at time t equal to 0 with an amount A0, after one half-life, you have half of what we started with. After another half-life, you have a half of what is left. So you have only now a quarter of the original. After another half-life, after 3 half-lives, you have a half of what you have here. So look at how the amount of substance decreases after each half-life. Let's now talk about carbon dating. The concept of half-life can be used to find out how old a particular sample is, a very commonly used phenomenon in archaeology. Now, each radioactive isotope has its own characteristic half-life. I told you that. Now, carbon-12 is the most abundant form of carbon in nature, and carbon-12 is a very stable isotope of carbon. But carbon-14 is a radioactive form of carbon. That also I told you. Carbon-14 is a radioactive form of carbon which decays by emitting a beta. Is that right? I showed you. Becomes nitrogen-14. You see, carbon emits a beta to become nitrogen, and its half-life is 5,730 years. What that means is, if I have a sample here, I take a sample here, suppose this sample now contains 50 grams of carbon-14. Now, its half-life is 5,730, means that after 5,730 years, the amount of carbon-14 in this will be 25 grams. You see, in 5,730 years, the amount of carbon-14 left will be 25 grams. That's right. That's what it means. And if you go another 5,730 from here, there will be only 12.5 carbon-14 left in the sample. That's the meaning in there. Now, plants and animals contain these two isotopes of carbon in the same proportion. They are found in the atmosphere. You see, in the atmosphere, carbon-12 and carbon-14 exist in some proportion. And plants and animals, that is each one of us and all the plants, also contains the same proportion of carbon-12 and carbon-14. Now, when a plant or an animal dies, it ceases to take more radioactive carbon. So when an animal or a plant dies, no more carbon-14 is taken from the atmosphere. That means this carbon-14 that is now in the death sample is now going to disintegrate, become nitrogen. See that? That means if you can take a sample that was dead long time ago, and if you can measure the ratio of carbon-14 to carbon-12, you can decide how long the sample has been dead. So as carbon-12 does not change and carbon-14 continues to decay. You see, carbon-12 is a stable isotope, it doesn't change. But carbon-14 in the death sample will keep on decaying. The ratio of carbon-12 to carbon-14 at the time of discovery of the fossil will give us information on how long ago was this plant dead, or how long ago was this plant living, how long ago was this dinosaur living. You see, if you can now take the bone of a dinosaur and measure the ratio of carbon-12 to carbon-14, you can very easily calculate how long ago this dinosaur lived. And this is called carbon dating. Let's do a small problem. The half-life of xenon 54-133 is 5 days. It means if you start with 10 grams of that substance, in 5 days only half of that will be left. If we start with 1 kilogram of this isotope, how much of the original nuclei are left in 15 days? Well, first of all, the half-life is 5 days. All right? How many 5 days are contained in 15 days? There are 3 of them. So 15 days make up 3 half-lives. Okay, so watch how I do this particular problem. The half-life of the material is T equal to 5 days. How many half-lives are contained in 15 days? There are 3 5s in 15. That means there are 3 half-lives in 15 days. So we go like this. When time t equal to 0, we start with A0 equal to 1 kilogram. Alright? After 1 half-life, now our 1 half-life is 5 days. So after 5 days, how much is left? After 5 days, you are left with half of 1 kilogram. That means 1/2 of a kilogram. So after 1 half-life, you are left with half a kilogram. Alright? After another half-life, you will be left with only half of this. After 2 half-lives, we are left with a quarter of we started with. I hope you understand. How much of this will be left after another 5 days? Now you have a quarter of a kilogram here. That is after 2 half-lives. 5 days. After 5 days, you have half a kilogram. After another 5 days, you got a quarter of a kilogram. And after another 5 days, you will be left with a half of this. What is half of 1/4? Will be 1/8 of a kilogram. So after 3 half-lives, that is after 15 days, you are left with 1/8 of a kilogram. Now, you can actually do any problems using the half-life like this. Alright, I would like you to practice these kind of small problems. I'm going to record a second part of this lesson and I will see you for that later.